Oh mon dieu! I discovered the spontaneous disintegration of some elements into smaller pieces!
You should call it radioactivity, ma chérie!
I've done it! Our great country can avenge the deaths of our soldiers. Down with Japan!
What have you done?
I've produced plutonium.
Now I shall create the atomic bomb. Victory to the Manhattan Project! I'm sure you are all wondering what those people were talking about. My team and I will explain the mysteries and wonders of nuclear chemistry. Let's start out with radiation. First, there's natural nuclear reactions, which is radioactivity that occurs naturally without human intervention. Some examples would be alpha emission, in which the nucleons are rearranged. Nucleons are nuclear particles. Beta emission is emission where the mass number is unchanged and the atomic number goes up by 1. Gamma emission is extremely dangerous emissions that have no mass or charge. Lastly, fusion is the fusing of 2 or more lighter atoms into a larger one. This leads us to ionizing versus non-ionizing radiation. Ionizing radiation is radiation that has sufficient energy to change molecules or atoms into ions. Non-ionizing radiation cannot change molecules or atoms into ions because it is too weak. For all these natural reactions, there are different types of particles involved. These include alpha, beta, gamma, neutron, positron, and proton particles. You might be wondering when these particles are used. Sometimes the nucleus becomes unstable because the neutron to proton ratio is incorrect, throwing off the balance. Radioactive elements are elements with an atomic number above 83. Radioactive decay is an attempt to correct the ratio of neutrons to protons. There are 2 types of this. The first would be alpha decay. This happens to nuclei with atomic numbers greater than 83. Beta decay happens to nuclei with high neutron to proton ratios. Artificial radiation is radioactivity that is produced by bombarding or striking a nucleus with a subatomic particle. This does not occur naturally. Fission is the artificial radiation that occurs during the splitting of a large atom into 2 or more smaller ones. An example of this would be gamma radiation.
Now that we know all these different reactions, we can take a look at writing equations. I know it sounds hard and awful, but you'll be pleasantly surprised that it's very, most simply, addition, subtraction, and some common sense regarding the periodic table. Let's look at an example. For this question, we can see it's an example of alpha decay because of this alpha particle. On the product side, we can see a neutron being emitted. Now, let's make sure we know a couple of things. There are 2 numbers here near the elements. At the top left, we have the mass number, which is protons plus neutrons. At the bottom left, we have the atomic number, or protons. What we do is we subtract going from left to right. And we get that 10 minus 4 is 6, and 5 minus 2 is 3. But we can't stop there, because we still have this neutron particle, and we have to remember that the sums here, or the differences, must be equal. There has to be 6 here for the left top and 6 here for the left top. And since we have a 1 here, this means the mass number has to be 5. But since there's just a 0, we can leave a 3 here. And now we refer to the periodic table and see what has a atomic number of 3. And we get lithium, which means the answer to what radioactive isotope is produced in this following bombardment of boron is lithium. Now let's take a look at an equation with a beta particle. The setup looks slightly different from the other question which had an alpha particle, but fear not, fellow chemistry compatriots, we can solve this quite simply. First, on the reactant side, we write CO for cobalt. And a side note about that, as the question asked for the beta emission from cobalt-60, the 60 here tells us the mass number. And now we can write the mass number there, and the atomic number, which says it is 27. Now we write the arrow associated with chemical equations, And then we draw the beta particle. And now we just do simple subtraction. We get 60 for the mass number and 28 for the atomic number, because 27 minus -1 is 28, not 26. And now we look here for the atomic number of 28 and we get nickel. Our final answer is nickel. So we have been subtracting all this time, right? In alpha and beta equations, you subtracted the mass and atomic numbers from left to right. But there is an exception to this rule. The exception would be gamma radiation. Here, you would add the mass and atomic numbers instead of subtracting. So 31 plus 1, 32, 15 plus 0, 15. You still get phosphorus, and you put a gamma particle here. And that would be the exception to the rule.
By now you may be wondering what in the world this is possibly used for. Here are a few applications. The most well-known application is nuclear bombs. Nuclear chemistry is a very powerful chemical source that is not to be reckoned with. There is a lot of science and research behind nuclear bombs, but to simplify, they use the energetic output of nuclear fission, which produces massive explosions. These are not to be confused, however, with hydrogen bombs, which use both fission and fusion as their power source. Another application is quite the opposite of destructive bombs. In fact, nuclear chemistry is often exploited in medicine as well. Radiation therapy is a common example. It is a type of therapy for cancer patients that uses rays. These rays consist of small particles called photons that attack the tumor. These minute subatomic particles remove electrons out of the tumor cell atoms and destroy larger molecules within the cells by destroying smaller chemical compounds. Another example are PET and CAT scans. These use scans to take accurate pictures of internal organs or structures within the body without causing any physical damage. CAT scans use X-rays, but PET scans use a radioactive material called a tracer, which allows doctors to see how body tissues absorb and use different chemicals. A common example that you see every day is smoke detectors. There was actually a lot of research in nuclear chemistry that went into your detector. There are two types, ionization and photoelectric. Ionization detectors use a small amount of radioactive material to make the air inside a sensing chamber conduct electricity. When smoke particles enter the chamber, they interfere with the conduction of electricity, reducing the current and triggering an alarm. However, photoelectric detectors contain a small light source that shines into a dark sensing chamber. This chamber contains a photoelectric cell which converts the light into a small electrical current. When smoke particles enter the sensing chamber, the light is reflected off of the particles, striking the cell and increasing the voltage generated by the cell. This then triggers the alarm.
Make sure when you're doing nuclear chemistry that you don't expose yourself to any harmful radiation.